Usually when we try to visualize something fundamental about the universe, there's this comforting expectation of perfect, clean geometry.
Right, like everything should just make sense on a grid.
Exactly. Imagine drawing a completely straight line with a ruler on a blank sheet of paper. You put the pen down, trace the edge, and you have this perfect, absolute representation of distance. It's binary, clean.
But then, try to draw that exact same straight line while sitting on a roller coaster that is actively plummeting toward the Earth.
Yeah, that's not going to work out so well.
No, and especially when you also try to account for the fact that the light hitting the paper from your pen is actually on a time delay. Suddenly that straight edge is, well, it's completely useless. The visual landscape just becomes entirely murky.
And untangling that web is our mission today. Welcome to this deep dive. Today we're pulling from a highly original and honestly somewhat rebellious physics draft.
Rebellious is a good word for it.
Right. It's titled Draft. Einstein Slacking 128 Praising Mr. Lorentz. And our mission for you today is to figure out if mainstream physics has been visualizing space, time, and the speed of light, completely wrong for the last century.
Because the author argues that we've all been missing this very simple mechanical trick of perspective, one that fundamentally alters how we should be looking at Einstein's special relativity.
So to set the foundation for you, we're going to dive headfirst into one of the most famous classical thought experiments in physics history.
The moving train.
Yes, the moving train. We'll use this to question the visual mechanics behind relativity and to explore why the author believes another physicist, Hendrik Lorentz, deserves way more credit for mapping out the sheer delayed messiness of our visual reality.
Yeah, let's jump right into that core scenario.
Okay, so imagine a train car hurtling through an electromagnetic field.
Which we can just think of as space, essentially.
Right, space. And the train is moving at 60% the speed of light, so 0.6 c. Inside this train, standing perfectly still on the floor, is what the author calls a red dummy figure.
But there is a specific catch here.
Yeah, this dummy has a height of exactly 0.
Wait, 0? So it's basically a two-dimensional point.
Exactly, just a point on the floor. Now imagine a beam of light dropping straight down from the ceiling of the train, aimed directly at this red dummy.
I mean, on paper, a light beam falling from a ceiling to a floor sounds like a simple vertical line. But the author argues that treating it as a simple vertical line is a massive conceptual trap.
To explain the trap, the text uses this really great analogy of a ferry crossing a river.
Oh, I love this one.
Yeah, so if you're in a boat and you want to cross a fast-moving river to reach a dock that is perfectly opposite you on the other bank, you can't just point your boat straight across water and hit the gas.
Right, because the current will just sweep you downstream.
Exactly, you'd miss the dock entirely. To actually hit that point directly across from you, you have to angle your boat upstream. You have to actively fight the current.
And the light dropping from the ceiling in our moving train acts just like that ferry.
Because it has to keep up with the train.
Right. For the light beam to successfully hit that red dummy on the floor of a train, rushing forward at 0.6 c, the light itself must have a forward horizontal component just to keep up with the physical movement of the train.
It can't just move down.
No, it has to move forward and down simultaneously.
Because the total speed of light is this absolute unbreakable limit. So any speed spent moving horizontally with the train actually subtracts from the vertical drop. The author calls this the Pythagorean budget.
The Pythagorean budget. That's a great term. You can think of it in terms of the basic geometry.
Right.
If your absolute speed limit is 1 and you spend 0.6 of that budget moving horizontally to keep up with the train, the math dictates that your remaining apparent speed for the vertical drop is only 0.8 c.
So the faster the train moves forward, the less speed is budgeted for the light to actually travel from the ceiling to the floor, at least from the perspective of an outside observer.
Yeah, it creates a strict physical limit. The light is forced to split its finite velocity between moving forward with the system and moving downward toward the target.
But hold on. Okay, let's unpack this. If I drop a tennis ball on a moving physical train, it falls straight down to my feet.
Right, it does.
Because the train car, the floor, the ceiling, the track, they're all moving together in one unified system. So if the observer is inside the train, why does the light have to play catch up at all? Doesn't the person inside just see it drop perfectly straight down?
You're hitting on the core issue here, but let's push it further. The frame of reference dictates the visual reality.
Yeah.
But we often forget that our visual reality is not instantaneous.
Right.
If you are standing on a spinning merry-go-round and you throw a ball straight across to a friend, The ball doesn't look like it's traveling in a straight line to you.
Oh, because I'm rotating.
Exactly. From your rotating moving perspective, the ball appears to curve dramatically in midair.
Even though someone standing on the solid ground next to the merry-go-round sees the ball travel in a perfectly straight line.
Yeah, that's the Coriolis effect.
My visual frame is rotating relative to the object in motion.
And applying that to light is where the paradigm shifts. A light beam traveling through the electromagnetic field will appear to take an altered, almost curved path when viewed from the extremely fast-moving frame of the train.
Because the light doesn't instantly connect the ceiling to the floor.
Right. It takes a physical amount of time to make that journey.
Which means the delay of time changes the geometry. This actually brings up another visual analogy from the text that I think perfectly illustrates the delay.
The microscope one.
Yeah.
Yeah.
Imagine you're looking through a high-powered microscope. You've got a prep slide. And on that slide is a tiny drop of water with some pollen suspended in it. Think about the physical state of that setup. The microscope, the glass slide, the table it's sitting on, the room, your physical body, and the retina of your eye.
They are all connected.
Right, and moving perfectly together as the Earth hurtles through space and rotates on its axis at roughly 1,000 miles an hour.
It is a highly dynamic, high-speed system that human perception incorrectly flags as entirely static.
Exactly, so the light bounces off the pollen on the slide. But it does not reach your eye in 0 seconds.
It takes time.
It has to travel up the physical tube of the microscope. By the time that specific photon of light actually hits your retina, the Earth has rotated. You, the microscope, and the slide have physically moved a microscopic distance through space.
So the light left the slide at a certain time in the past.
And it arrives at your eye in your present. You are receiving a continuous stream of delayed information.
What's fascinating here is how the author applies this exact mechanism to the observer inside the moving train. He refers to them as the train king.
The train king.
Yeah, the train king assumes that because they are standing perfectly still relative to the floor and the ceiling, they are seeing the train exactly as it is in that exact millisecond.
But they aren't.
No, because light takes time to travel from the ceiling down to the train king's eye. The observer is continuously being hit by light that originated from a spatial location in the past.
So when the train king looks up at the light fixture on the ceiling, they aren't seeing where the fixture is right now.
Right.
They're seeing where the fixture was a fraction of a nanosecond ago, back when the physical train was slightly further back on the train tracks.
Assuming the light just moves perfectly straight up and down in a moving train is just this convenient visual fantasy.
It completely ignores the reality.
Yeah, it ignores that the train king is effectively driving forward into the light that was emitted from the ceiling in the past. The light's path, from the perspective of the moving observer, is a complex trajectory of delayed information catching up to a moving target.
But wait, if theoretical physicists have been building on Einstein's light clock models for a century, you're telling me they all just conveniently forgot that light takes time to travel?
That's the argument.
That seems like a massive historical oversight. What's the author's actual proof that they missed this geometric reality?
Well, the author points to a massive historical blind spot involving an 18th century astronomer named James Bradley.
Okay, James Bradley.
When Bradley was trying to observe starlight through his telescope, he realized a mechanical problem. He couldn't just point the telescope directly at where the star appeared to be.
Why not?
Because the Earth was physically moving through space at high speed in its orbit, Bradley had to actually tilt his telescope forward slightly to catch the starlight down the tube.
Oh, like holding an umbrella slightly forward when you're running in the rain?
Exactly.
If you hold it perfectly straight up, your forward momentum causes you to run right into the raindrops falling in front of you.
The mechanics are identical. If Bradley didn't tilt the telescope, the Earth's movement would shift the physical tube out of the way before the photon could reach the eyepiece at the bottom.
Wow.
The author argues that theoretical physicists, when constructing the famous light clock thought experiments for special relativity, completely ignored Bradley's telescope.
They ignored the necessary tilt.
Right. They drew diagrams where the light inside the moving train acted as if the delay of observation simply didn't exist.
You know, here's where it gets really interesting. It's funny, we actually accept this concept intuitively in pop culture, even if we don't realize it.
What do you mean?
Well, the author points out a contradiction in sci-fi movies. When the captain of a starship yells engage and the ship accelerates to near light speed, the stars out the window don't stay as neat little white dots.
Oh, right, they stretch.
Yeah, the geometry of the room, the view out the window, it all distorts, stretches, and bends. We fully expect the visual reality to warp because of the extreme speed.
It highlights a deep cognitive dissonance. We accept profound visual distortion in fiction because it inherently makes sense that moving at the speed of light would mess with how light reaches our eyes.
Right.
Yet we stubbornly cling to rigid, straight-line geometry in our theoretical physics diagrams.
The author even gets a bit cheeky here, suggesting that the mainstream physics industry is almost suffering from a kind of Stockholm syndrome.
Stockholm syndrome, that's strong.
Yeah, but he means generation after generation of physicists have blindly accepted these perfectly straight, rigid line visualizations without stopping to question the fundamental delay of information.
They just learned the clean geometric diagrams in school.
Exactly. They liked how easy they were to teach, and they became hostages to a flawed map. They sacrificed the messy truth for theoretical simplicity.
Which brings us to the ultimate synthesis of the author's argument, and why the piece is titled Praising Mr. Lorentz.
Hendrik Lorentz.
Yeah. Lorentz is famous for the Lorentz contraction, a mathematical formula showing how objects physically shorten the direction of motion as they approach the speed of light.
Okay.
Historically, this is often treated in textbooks as a mathematical band-aid.
Right. People assumed Lorentz just created a clever equation to force the confusing results of the famous Michelson-Morley experiment to make sense.
Like he was just fudging the numbers.
Exactly, just fudging the numbers to save the classical laws of physics.
But the author of our source argues that Lorentz wasn't just creating a hack. By charting out how the speed of light must be mathematically budgeted, that Pythagorean limitation we discussed with the train and the fairy Lorentz was actually mapping out the fundamental delay of information.
Oh, wow.
He was mapping what the physicist Hermann Minkowski would later call the past light cone.
Meaning the expanding sphere of light from an event in the past that is only just now reaching the observer.
Exactly. Lorentz realized that what you measure and what you actually see are fundamentally distorted by the fact that you are physically moving while the information is taking time to travel to you.
So the visual distortion, the necessary tilt of reality Lorentz, had the conceptual breakthrough figured out.
He did. The tragedy is that he just lacked the modern vocabulary to explain it clearly to his peers.
Well, yeah, I mean, he lived in the late 1800s and early 1900s. He didn't have the language of the digital age. And this is where the text introduces a modern metaphor that perfectly maps to this physics problem.
Video game server lag.
Yes. Video game server lag. It's such a relatable way to put it.
It translates a highly abstract concept into a frustratingly real, everyday experience.
If you've ever played a fast-paced online multiplayer game, you know the mechanics of server lag. You are running behind a concrete wall to take cover. On your screen, which is your local frame of reference, you are completely safe behind the wall.
Right, you're safe locally.
But then, you suddenly take damage and get hit. How does that happen? Because on the central server, the information about where you are and where the enemy's bullet is took a few milliseconds to update.
The local client and the absolute server fall out of sync.
Exactly. The enemy saw you where you were a fraction of a second ago. They shot at that past ghost of you, and the server calculates that they hit you. Your visual reality on your monitor completely disagreed with the underlying reality of the data transfer.
And that mechanism is exactly what is happening inside the Lightspeed train.
It's the exact same thing.
The train king thinks they see the light traveling in a perfect straight line from the ceiling to the floor, but they're experiencing reality lag.
Reality lag.
Yeah, the light hitting their eye right now originated from a different spatial location in the past. The visual reality they're experiencing is just a delayed rendering of the true physical events.
The author argues that Lorentz almost had this perfectly articulated. If he had possessed terms like online gaming lag or generative AI to describe how delayed data creates a distorted, rendered reality for the observer, the whole history of physics visualization might be entirely different.
He could have just said, look, the measurements look weird because the observer is experiencing server lag.
That would have saved everyone a lot of headaches.
If we connect this to the bigger picture, the takeaway here is a profound lesson in a classic philosophical concept. Not confusing the map with the territory.
In physics, it's incredibly tempting to draw a simple X and Y graph. We put a point on the paper and say, this is an event. That graph is the map.
Right.
But the territory, the actual messy lived experience of the universe, requires us to account for the human observer.
Just because we can draw a perfectly straight line on a piece of paper between 2 points doesn't mean that's how a human observer or even a highly advanced sensor actually perceives the delayed information arriving at them.
The map is instantaneous.
But the territory is hopelessly bogged down by the speed of light.
So for you listening right now, it means that a simple thought experiment about a moving train reveals massive underlying assumptions about how we visualize reality itself.
It really does.
When we swap out those perfect, clean, geometric straight lines for the messy, delayed reality of server lag and the Coriolis effect, we get a much richer, much more accurate view of the universe.
Absolutely.
We realize that our intuition is constantly being hijacked by our own local frame of reference. The map is not the territory, and the straight line is rarely straight.
It forces a necessary humility about our own perceptions. Consider this. If everything we see is just a delayed rendering, the server lag of the past, what does that mean for the scale of the universe?
That's a huge question.
When you look up at the stars in the night sky, you aren't seeing them as they are. Some of those stars might have burned out and died millions of years ago.
But in our local rendered reality, the light is just now arriving.
Exactly. They're still shining for us. You aren't just looking through vast stretches of empty space. You are literally living inside a delayed simulation of time. Every single thing you experience is just a ghost of the past finally catching up to you.